Today we're going to take a look at the dot product, which is also known as the scalar product. So you guys have a couple things in that, well, one thing that you're going to paste in, two things. So our definition of a dot product is if we have two vectors, A, B, we multiply the A and the B, so the x components times the y components. If the dot product is 0, then we say the vectors are perpendicular, and if they're scalar multiples of each other, then they are parallel. So first of all, let's just write an example on here to make sure that we're okay with what the dot product is. Let's let P equal 2, 3. And let's let Q equal 1, 4. So P times Q, 2 times 1, so you take the x components, plus 3 times 4. So 2 plus 12. So our dot product would be 14. So we're going to take a look at a couple of these and decide if they're parallel, perpendicular, or neither. So this first one, well, let's see if they are parallel or perpendicular. We'll do the perpendicular test. So 6 times 2 plus 4 times negative 3. Well, that's 12 plus negative 12. So our dot product is 0. So they are perpendicular. So the second one, let's see if they're perpendicular. So 9 times 3 plus 15 times 5. So 27 plus 75. So 102, so no to perpendicular. Well, if they're multiples of each other, well, how do we get from here to here? Well, that's times 1/3 times 1/3. So they're both the same, so these are parallel. And then let's see, this works in 3D too. So our perpendicular test, 1 times 0, 3 times 5, 2, negative 2 times 4, 0 plus 15 minus 8. So our dot product is 7, so they're not perpendicular. Well, let's see, that would be times 0. Well, that's not the same, so they're not parallel. So these vectors are neither. All right, so the last thing that we're going to take a look at is, let's say vectors A and B have length 5 and the square root of 7. The angle between them is 110. So the angle between them is 110 degrees. And our goal is to find that dot product, A times B. Well, the tricky part here is they're not in component form. So what we are going to do is we're going to actually draw these vectors out. So let's draw one. So we know that that's 5. And then the other one, it's 110 degrees. So that one's the square root of 7. And so we know that angle is 110 degrees. Well, in component form, if we just drew this one this way, it's 5, 0. So this other one here, though, we don't have the x and y components. So we have x and y. Well, that's a right triangle right here, and if that's 110, this would be 70 degrees. So we could set up some trig functions. Opposite is y, the hypotenuse. So the sine of 70 equals y over the square root of 7. So multiply by the square root of 7. So the square root of 7 times the sine of 70 equals y. And then let's see our x adjacent over hypotenuse, the cosine of 70, x over the square root of 7. So multiply by the square root of 7. So the square root of 7 times the cosine of 70 equals x. So let's see here. We can go to Desmos. Make sure I got to switch this to degrees. So we have the square root of 7 times the sine of 70. And we have the square root of 7 times cosine of 70. So we have 0.9. So our x is 0.9 and our y is 2.5. So x equals 0.9. So we can go back up here. So times x is 0.9, y is 2.5. So we have 5 times 0.9 plus 0 times 2.5. Well, 5 times 0.9, we got 4.5. Oh, we should have been able to do that. And there is our dot product. So we're going to take a look at another one here. Using that dot product. What if we had to find the angle between maybe it's not using the dot product. Sorry, but some of this trig here, see what we can figure out. Between 3, negative 2. Oops, that's supposed to be a parenthesis. And 1, 7. So if we were to draw a picture of this, (3, negative 2) and 1, 7, which over 1 would be up here somewhere. So 3, negative 2, 1, 7. Well, we just have two right triangles here. So we could use that inverse trig, so opposite over adjacent. So the tan inverse of negative 2 over 3. So let's see, functions negative 2 divided by 3, negative 33 degrees. That makes sense, it's going down from the x-axis, but we could just say that this is 33 degrees. And then this one, the inverse tan of opposite over adjacent. So the inverse tan of 7. (81.9 degrees). So this angle, 81.9 degrees, well, the two of them, we'd have to add them together. So 81.9 plus 33.9 for 114.9 degrees. So this trig is going to start coming back to us. And the third example that we're going to take a look at, let's say we had to find the measure of ABC. If A is 2, -1. B is 3, 4. And these are coordinates. And C is -1, 3. So let's see. 2, -1. 3, 1, 2, 3, 4. There's B, -1, 3. And we are trying to find the angle ABC. So we are trying to find this angle. Well, again, we don't have side lengths, but we could set this up to vectors, A to B. So A to B, we go over 1 and up 5. A to C, backwards 3 and up 4. And then C to B, or B to C, 3 to -1, backwards 4 and down 1. And now we have to do the Pythagorean theorem to find those sides. But let's see, so 25 and 1 squared plus 5 squared. So that's the square root of 26. -3 squared plus 4 squared. Well, that's a 3, 4, 5. Let's see, -4 squared plus -1 squared, square root of 17. And now to find that angle, we could use that law of cosines. So if we want to find angle B, 5 squared equals the square root of 17 squared plus the square root of 26 squared minus 2 square root of 17 square root of 26 times the cosine of B. So we have 25 equals 17 plus 26 . Again, we just combine those first two together. So 17 plus 26, 3643. Minus 43. So 25 minus 43, -18. Equals all of this. We got to divide by this. So let's see, if we put that in there, -18 divided by -2 square root of 17 square root, oops. Square root of 26.428. And then we do the inverse cosine to find that angle. So 43.3 degrees. We have it there.